Okay,
Okay,
can you see my presentation?
Yes, so no Marcin lecture will come and then the panel discussion because we miss, Peter is with us, but we miss Vera. They had an accident with a cat and Ted Goranzon had some trouble with his computer, so they will come later. So therefore the program is the following one. Marcin lecture is coming, you see already the title, and then we will have the panel discussion later. Marcin, please.
Okay, thank you. And main points are antinomy of structuralism. Structuralism, did it ever happen? Structure and symmetry in science, measuring symmetry by groups. Symmetries in physics, chemistry, and biology. Antinomies of symmetry and information. And then seventh question, are snowflakes hexagonal? So I will skip some slides because Dennis already talked about enantiomers or in the context of our enantiomorphic lectures. The thing is that this mirror symmetry played a role in basically all history and even in prehistory of humanity. Peter already talked about this, but this is one of the subjects of my special interest, is the role of mirror symmetry in religious beliefs. So for instance, Normans, as far as from archaeological analysis we can figure out, is that they believe that the world of afterlife is an enantiomer of this life, even before they started to use mirrors. Yeah, so this belief came from the observation of the reflection of the world in the sacred bogs. Now, these wetlands gave them image of different world, and they believe that that this afterlife has this enantiomorphic form. This is one of the reasons is about, for instance, what Peter was mentioning was the position of the swords in the graves. So normally sword was actually on the left side, because when you draw sword, you draw with the right hand and you draw it from the left side. And in the graves, swords were located on the other side. With what was additional confirmation was exclusion from the rule that there were some very rare cases that sword was put on the left side, on the right side, and most likely this was for warriors who were left-handed. But anyway, from a very early time, there was this fascination of the world, which would be with the reflection through the mirror. One of expressions of this interest we can find in the works of Immanuel Kant. Yeah, he was reflecting on this in 4 of his most important works. He was talking about incongruent counterparts. For me, here is like, if you observe some incongruent elements in Dennis's lecture and my presentation, this will be like this mirror reflection. So not exactly the same views, but basically referring to the same issue and following the same path of thinking. So here is basically, I would like to start from antinomy of structurality. Here is Dennis mentioned this, that structuralism is traced usually to the work, modern structuralist, to the work of Ferdinand de Saussure in linguistics. What was the key point from methodological point of view? It was the distinction of two fundamental types of inquiry, diachronic and synchronic. And his point was to go from a diachronic historical view of language to synchronic view, which was like cut and looking at the structure at one particular time. They are not diachronic, but synchronic. This was, in some sense, revolutionary view in the late 19th century, but this spelled some kind of doom on structuralism as a way of thinking in especially humanistic philosophy. But I'll talk about this later. So here we have this first antinomy is in two different ways of looking at inquiry. One is that we are looking from the point of view, historical point of view, or from the dynamical point of view of evolution or revolutions. The other one is focusing on something which is frozen into structure. This belief in this synchronic or non-historical or non-evolutionary approach in structuralism caused lots of problems. And even now, many philosophers who announce that they are post-structuralists, they just don't understand what structuralism is. So here is one of these antinomies which I will try to remove, to solve. Structuralism was very influential. Here again, Dennis was talking about contributions by Hermann Weyl. His very famous book. This book basically promoted the idea of structural study, structural methodology outside of science. In science at this time, nobody was even talking about structure because science was already study of structures. There was no need to talk about some kind of special methodology. So another very important contribution was by Jean Piaget, Structuralism, which was published in French in '68 and translated into English into 1970. These two books were extremely influential from the point of view of way of thinking in humanities and in social sciences. I will not go into details of this, but there was some kind of backlash. After some time where structuralism was like dominating approach to humanistic and social science studies, there was this conviction that structuralism does not allow study of transformation. And of course, this was coming from this from the sources where you can see that the Saussure made a revolution to go against historical view of linguistics, but it doesn't mean that structuralism has to assume, has to exclude evolutionary or historical point of view. And this can be seen in the role of study of structures, the study of symmetry, which basically was promoted and was initiated on big scale by Felix Klein in 1872 in his Erlangen program. Yeah, this was the idea that symmetry means basically invariance with respect to a group of transformations. Klein has intention to unify geometry. There were many forms of geometry, projective, affine geometry, synthetic geometry, and the question was, why geometry? What is common for all this? So he proposed this, and the easiest case from which we can start is to talk about mirror reflection. Now, when we have hard sign, it is symmetric with respect to reflection with respect to this axis. This vertical line describes it's an axis of symmetry. When we flop this image around this axis, we get exactly the same height. So what Klein did, he said, okay, we don't have to consider only mirror reflection, only rotations. We can, in general, consider transformations, preserving distances, or which we call in mathematics isometries. And then these transformations form what in mathematics is called group. It was more or less the same time when group theory was clearly formed. It had sources much earlier, for instance, in works of Legendre, before everything in contribution of Galois. But about group theory, we can see that it was about 1870 where it started to develop. Right now, it is one of the main parts of mathematics. So here we had this mirror reflection, which was one type of symmetry. We have, for instance, rotations of a triangle. Here we have this triangle, and we can consider not only, for instance, mirror symmetry with respect to this axis, but we can rotate this triangle by 120 degrees. Actually, what I should say, we can rotate plane by 120 degrees, and the triangle will remain unchanged. So in a quite short time, the idea was moved to physics. The most important, actually, one of the most revolutionary moments in physics was when Emma Noether proved her very famous first and second theorem. What is so crucial is that Noether showed that why we are, I will of course paraphrase, it is not what the theorem is saying. Why we consider energy, why we consider momentum, why we, for instance, in kinetic energy, we have mv squared divided by 2. Why energy, not mv cubed or mv to the power of 4 divided by 2? And the reason is that if we want to have physical theory invariant with respect to change of observer, where change of observer will be classical physics, it will be Galileo group transformations from one observer to the other who is moving, but moving with constant speed along the line. Then if we want to have this invariance of description, we'll find some conserved magnitudes. And one of these magnitudes is, for instance, energy. Energy is conserved. It's not that we discover energy conserved. We are choosing energy to be magnitude which is conserved if we want to have description which is which is invariant with respect to time scale. Means that what theory will tell us, if we start observing a world today, it will be the same when we start observe world tomorrow. Otherwise, of course, it will be chaos. If every day we have different physics, there will be no point in doing physics. So this was basically, I would compare Netter's theorem to work of Copernicus. It is true that Emma Netter was not first who observed some connections. These connections were coming from many works in 19th century, but usually they were, okay, we have transformation or change of the time, then we have energy concern. If we consider change of position of observer, we will have momentum concern. So pieces of this could be found in several works before, but what Emma Netter did, she did it for general. Whenever we have a group of transformations, it is here that this group of transformations has to be continued and so on, but these are details. Then we'll have some magnitudes which are conserved. And of course, this magnitude is showing us you should study energy, not mv cubed divided by 2, because this is what will be conserved when we have conservation in time, and also what will be the same when we change observer. When I say it will be the same, it will be sometimes it is covariant, so that it can change, but we know how we can change. Okay, so this was a revolution which made symmetry a central concept in physics, and it stays for all the time. Now, a few words, what exactly we are talking about this. So you can see here this illustration by Da Vinci to Vitruvius' work, where we have human body, and you can see that this human body is symmetric with respect to mirror reflection when we are flipping around this axis, which is vertical. Then we can have also reflections with respect to this blue axis. You can find, for instance, fascination with symmetries you can find in many cultures. So here I'm showing, of course, these lines, this is my addition. Sengai Gibbon's famous Zenga, where we have square, triangle, and circle. Now this here you can see that here we have some symmetries with which are related to mirror reflection of the square. Here for triangle. For circle, I cannot graph all axes of symmetry because there are infinitely many of them. And now how it works. Suppose we have a triangle. Now then we can consider what are these transformations of the plane which will keep this triangle unchanged. So we can see that this will be rotations. Rotation rho 1 is rotation by 0 degrees. So of course it is like trivial transformation. But rho 1 is transformation by 120 degrees, rho 2 by 240 degrees, and then we come back to rho 0 if we add to this 120 degrees. But we have also symmetries which are related to mirror symmetries. You can see here what are these, and they are showed here. Then what is happening when we consider these transformations which are involved, then we can combine, we can take one transformation and then the other. It turns out, for instance, we don't need rotations separately. We can use only mirror reflections and we can get all rotations. this structure of transformations, when they are combined, forms a group which has this table. This group is called D3. There are some differences in terminology. I follow here a description that this is D3. It is a group of symmetry of regular triangles, means equilateral triangles. D4 is for square, D5 is for pentagon, and so on. Sometimes you'll see that it is changed because here we have that we have 6 elements. So in some places you will see this as D6, but this is a matter of just notation. So here we have table of these operations. If you combine, for instance, mu2 with mu1, you get row 2, means these 2 mirror reflections give us rotation by 240 degrees. Row 1 is 120 degrees, row 2 is 240 degrees. So this is this group which describes symmetry of a triangle. Then we can talk about symmetry of a square. Now here we have rotations again. Row 0 is 0 rotation, means identity transformation. But then we have mirror reflections with respect to vertical and horizontal axis, but also symmetry with respect to diagonal axis. And then we get this table of transformations. When you combine, for instance, row 3 with row 2, you get row 1. If you get row 2 with mu1, you get mu2, and so on. So this is table, like table of multiplication, which you had to learn in elementary school or kindergarten. This is table for the group, which tells us how different transformations which preserve given structure, how they can be combined. So as I said, Emmy Netter's work was like a revolutionary point in physics. And in 1972, Philip Warren Anderson, who was Nobel Prize laureate in physics, wrote in a very famous article, "More is different." It is only slightly overstating the case to say that physics is a study of symmetry. So we can look at development of physics from the point of view of different groups which are used. So for instance, classical theory is basically theory which is invariant with respect to Galileo group. Of course, Galileo didn't have any idea about groups. It was just talking about what he was describing, and then we can, in modern language, we can describe this as Galileo group. So transition from Newton's classical mechanics to Einstein's special relativity is simply change of the fundamental symmetry group from Galilean group to Lorentz group. This is why, for instance, when I read articles, sensational articles in media, that somebody was saying, oh, if we add the formula given by Einstein, E equals mc squared, we add some epsilon plus epsilon, we can explain dark matter. There's no point even reading something like this, even if it comes from quite respected universities sometimes, because the issue is not what you add to something or you change something like this. You have to tell me what group of symmetry you are introducing, and then we can talk about change. And thus far, even if people tried hard, nobody found any violation of Lorentz group. So, of course, if somebody can prove that we have to change Lorentz group to something else, this will be huge revolution. But by adding some epsilon to some point, this is just childish play. It is not something that we can expect any real change. So Dennis was already talking about symmetry. We have contributions from Pasteur, but one of these important contributions, but which are bring us to the next antinomy in symmetry, is work of Pierre Curie, who introduced this principle of dissymmetry. Only broken symmetry can produce broken symmetry. The issue, sometimes there are confusion. So what is important, symmetry or this symmetry or breaking symmetry? And I will try to resolve this antinomy by showing that both are important. We cannot talk about just symmetry, and actually I will try to prove or to demonstrate there is no asymmetry. There's only change of symmetry. So one more and last comment about problem with structuralism. As I wrote in my main points, did ever structuralism appear in humanities and social sciences? My claim is not. When you read the only person from this side who understood these issues was Piaget. What Levi-Strauss wrote, he didn't have any idea what this symmetry is. He was using some examples and he was combining it, but it's not difficult to attack him because he didn't get any new results within his analysis. Because he did not use anything new about what is, he was just recovering what is already known. So my claim is that right now there is revival of structuralism and the so-called neo-structuralism. My claim is it is just age of beginning of structuralism in humanities and social sciences. The key point is what so-called structuralists, especially of French school, missed was that they believed that concept of the structure is rigid. And it would be like complaining physics is rigid, nothing is changing, physics does not admit change. Nonsense. Now, structuralism means structure based on symmetry, is showing that we can describe dynamical change through symmetry, but of course, in this case, symmetry is not just spatial symmetry, but it is, we have to consider symmetry of space-time. So here is, I don't see any reason to worry about diachronic and synchronic antinomy, because there is no such thing. It is just that these are two faces of the same coin, and it is resolved by dynamical groups. And here we are coming to this another claim. Yes, you can enter the same river twice because you and the river are structures, not their components. So what Heraclitus was saying was, okay, water in river is changing. So you don't enter the river, you cannot enter the river twice. And the answer is no, you can't, because river is not water. It is structure. It is the way how water is flowing. So of course, when you look carefully at the species which Heraclitus, because we know very little about his real views, you can see that through this river metaphor, he wanted to express exactly the same. He was just counting on intelligence of the reader or listener, by that we will know that our common sense river is not what we before thought that this is water, but it is structure of the flow of the water. So Heraclitus was intelligent and he knew what he was saying. But then thousands, maybe millions now, people were reading him and they believe that there is some kind of strange thing in his thought. Now, another antinomy is that symmetry very often is understood as something which is related to human intentionality or to something which is artificial. Curie principle tells us that only broken symmetry can produce broken symmetry. In this case, why are symmetric objects more rare than those asymmetric, and typically they are products of human action? And this question can be answered after we associate symmetry with information. And it's interesting that the first partial answer was given by Gregory Bateson in his 1971 article, Re-examination of Bateson Rule. Marina yesterday was referring to exactly the same article, so I was happy to see that this article is of Bateson is appreciated, because this article is, I believe, one of the most important contributions of Bateson. And in this article, actually, what is interesting, we have that we have traditional definition of information included by Bateson, which says that information is that which excludes certain alternatives, which can be associated with Shannon and information theory of Shannon type. And then he introduces in this article a little bit less general than this famous formulation, but his original formulation of the definition of information as any difference which makes a difference in some later event. Later he cut out this because he could see that this can be in many different contexts. So what was revolutionary, that Bateson observed that breaking the morphological symmetry requires information regarding the direction of going out of the original symmetry. His article is referring to work of his father, William Bateson, who actually is famous mainly because he introduced his name genetics. But actually, William Bateson was a very deep thinker, and there is lots of very good ideas in his book, which was published in, I think, 1884. So Gregory Bateson is referring here that what is happening when we observe a violation or breaking of symmetry in organic world, that this is related to the fact that we have some breaking of symmetry, which can be associated with the transfer of information. If we don't have information, we will have symmetric case. There has to be outside source of information which is stimulating violation of symmetry. I will not refer to his main examples, but he is giving this interesting short description of the situation. How organisms, and you can see that organisms are growing with a number of cases of breaking of symmetry in evolutionary changes. How the original one cell of the organism is violating this symmetry. That Bateson is referring to what was determined, that this breaking of symmetry is through the point where spermatozoa are entering egg. So at the moment of creation of new organisms, where we have for instance, in more advanced cases, we have egg and sperm, that entering of sperm is indicating direction, and this direction gives us breaking symmetry, and then several other external influences are pushing this asymmetry further. Breaking of symmetry was at the time already in focus of physics, chemistry, biology, but based on association of breaking of symmetry with information was his original idea in 1971. This was something like very fresh and very new. Paraphrasing Anderson, we could say that physics is a study of symmetry and its breaking. Yeah, because actually this more is different article of Anderson is about breaking symmetry, not about symmetry itself. And the term breaking symmetry is confusing. Again, it causes a lot of confusion, especially outside of specialistic social environments where people are using it just as short way to express something. Because breaking symmetry, this word breaking looks like that we have symmetric object, then boom, symmetry is gone, and we have a pile of garbage. It's not this way. Yeah, so we have, in this case, we have that we should talk about the structure, partial order of symmetry. What we have transition. Breaking of symmetry is transition from one group of symmetry to another group of symmetry. Yeah, we have that in this case, we have, for instance, in some cases, we can have transition, like for instance, D3 can go to, sorry, D6 can be broken to D3. D6 is symmetry of hexagon can be broken to symmetry of a triangle. Of course, hexagon includes all the same transformations, and triangle has less transformations, and here we can have breaking symmetry. But breaking symmetry does not describe transition from symmetry of hexagon to symmetry of square. These two groups are incomparable. So symmetry basically is a matter of the degree. Yeah, so we have structure of subgroups. This structure of subgroups is not linear. It is ordered by the so-called partial order. Now, there are some subgroups which are comparable. One is subgroup of the other, but there are groups which you cannot compare. So when we see like Armstrong, who wrote very popular textbook on symmetry, groups and symmetry in 2010, numbers measure size, groups measure symmetry. I would agree with him, but with some small amendment. Numbers measure size. Subgroups of the group of all possible transformations measure symmetry. And here is, there is some kind of explanation why groups are so important, why we are talking in terms of groups and their subgroups. And the answer is very clear. Yeah, we know it for 50 years, that this structure of subgroups is most general possible, means the lattice which represents this structure, maybe this way, every lattice can be is isomorphic with sublattice of this lattice of subgroups. So this configurations of subgroups in general, when we have group theory, is most general of all possibilities. So we don't have to worry that at some point we'll have to move from groups to something else. And so here I was promoting this idea. Breaking symmetry means a transition from one symmetry to another of lower degree. Interestingly, this view can be seen in Bayesian article. Most famous are instances of breaking symmetry in physics, especially spontaneous breaking of symmetry, which are related to the issues of existence of particular forces in physics. This is some kind of like core of all physics is sitting in this. And this is just because we can observe that higher symmetry states are sometimes unstable. Small fluctuation can move system. Oh, this is so-called sombrero image of this. If we have particle can be, according to physical theory, can give the state of this particle can be solution of equation of this theory. But if you move it a little bit because of energetic issues, you'll have that this particle will go down. And then we have breaking of symmetry. Here, the state was symmetric with respect to reflection. Here we have broken symmetry. And we know that we face instabilities, and then they are producing the world we know. And finally, why is symmetry associated with human intentionality and artificial? It's because we recognize only some symmetries. And my definition of intelligence is that intelligence is the capacity to reduce complexity. And what we are doing, we are trying to find out what the simplest, most powerful symmetries we can observe in our environment. But we do not recognize more complicated symmetries. So here is example which I wanted to use is, everybody knows snowflakes have hexagonal symmetry. Here, and actually it's not necessarily true. Even in 19th century, this is a picture from catalog of snowflakes. There are symmetries which have different symmetries. For instance, here, these are symmetries of triangle. They are actually quite rare. We know exactly when snow forms this kind of snowflakes. It is in -2 degrees. Snowflakes are like this. It is only outside of this region that we have hexagonal snowflakes. There are snowflakes which have 12 fronts, which means that we have the 12 symmetry, but so we can go from hexagonal, we can go up in symmetry, or we can go down in symmetry. But this does not answer our question why symmetry is associated with human intentionality. And this is because in reality, only 0.1% of snowflakes exhibit D6 symmetry. It is just that when we look at snow and we can observe all beautiful snowflakes, we pay attention to snowflakes which have hexagonal symmetry, but we don't pay attention. Majority of them are not symmetric at all. Here you have picture of, for instance, this snowflake has symmetry with respect to this axis mirror symmetry, but it doesn't exhibit hexagonal symmetry. So here is not that symmetry is related to human observation or human intentionality. It is just that we humans select some form of symmetry which we prefer. So I will say that at the end, I wish I could ask Gregory Bateson in this case, whether he would agree with his definition slightly revised. Information is a difference in symmetry. Okay, that's all. Thank you very much.
Thank you. Thank you very much, Marcin.